A very good morning, good afternoon, good evening to all the participants, students for this course titled Multi-Criteria Decision Making, which is under the NPTEL MOOC series. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur in India. So, as you know, we are in the 6th week of the set of classes. Total number of week is 12, spread over 60 lectures, and each week we have 5 classes, each class being for or lecture being for half an hour. So, this is lecture number 30, which is the last lecture or the last class to complete the 6th week. The broader guidelines, broader ideas, broader concepts which we have been covering for a long time, for a lot of classes and lectures spread over the weeks are as follows: multi-criteria decision making, multi-objective decision making, which is more objective, continuous, mathematical express, easy to communicate, answers are easy to understand, and which we are covering now. Then there is multi-attribute decision making, multi-attribute utility theory, which is more qualitative, subjective, where trying to analyze the problems may be more intuitive in nature. The set of coverage or the set of topics covered for this 30th lecture would be Pareto optimality, Pareto curves, and some ideas about goal programming. Obviously, we will do problems accordingly. So, in the 29th lecture, which was the last one, we were discussing a problem where there were 3 decision variables x 1, x 2, x 3, and for simplicity we took them as discrete, and based on that we formulated functions f 1, f 2, f 3, and we were trying to analyze that how they would be considered, the concept of Pareto optimality and the idea that non-dominating and dominating concepts were being discussed. We will continue with that. So, again consider the same problem for ease of understanding. I am going to repeat it. So, you have 3 decision variables x 1, x 2, x 3, and they are discrete. X 1 is 0, 1, 2, 3, similarly for x 2 and also for x 3. The subject to condition, which we will mark in a different color green, is that sum of x 1, x 2, x 3 is 3, and the functions, there are 3 functions f 1, f 2, f 3 is as follows. The first one is x 1 square plus x 2 into x 3, second one is x 2 square plus x 1 into x 3, third one is x 3 square plus x 1 into x 2. Based on that, considering the sum is 7, we have this set of values for our analysis. So, the first column, second column, third column are the corresponding values of x 1, x 2, x 3, such that the idea condition that x 1 plus x 2, x 3 is met in all the cases, add up, and they all add up to exactly 3. Now, based on that set which are feasible, we find out f 1, f 2, f 3 as given in the last slide, which were these 3 f 1, f 2, f 3, and they have been marked in third column, fourth column, fifth column, and in the sixth column, last one, I have just added up the sum of f 1, f 2, f 3. And if you remember, we discussed what does this yellow cell mean, the blue cell, the dark yellow cell, and the green cell, and we discussed in details. This was for f 1, f 2. Similarly, the same table, but here now we are considering f 3 and f 1, again same concept of coloring, dark yellow, green, blue and yellow, and the analysis was almost the same thing, but I repeat it in order to make it much clearer. Finally, where we stopped the last class was now the comparison for the same table, comparison of F1 and F3, considering the coloring scheme was exactly the same, dark yellow, blue, yellow, green, and here on all these three examples the Pareto concepts was repeatedly mentioned by different comparisons. That is number 1. Number 2, the concept of indifference curve was also highlighted with this simple example, how they move parallelly. And remember, in this problem it was a maximization concept considering F1, F2 or F2, F3 or F1, F3, which is in this slide. The other two slides were basically corresponding to F1, F2 and F2, F3. So, all these functions were maximized. Now, where we left the last day, I will continue discussing there. Same problem, 3 variables x1, x2, x3 all are discrete and the values they can take are 0, 1, 2, 3. Sum of them has to be exactly 3. So, the set of values which we will consider for our analysis is given in the first column for x1, second column for x2, third column for x3, and check the sum of all these x1 plus x2 plus x3 is exactly 3. Similarly, f1, f2, f3 are the functions here marked in dark blue, and finally, on the right hand column the sum of f1, f2, f3 is given. Now, consider the green cell set of cells, the horizontal rows. There are 2 rows and considering the dark or the orange one, the light orange one, whatever you say. Now, consider we want to minimize F3, there is no more idea of maximization now. In all the 3 examples which we considered earlier, which was considering 2 at a time function or amongst F1, F2, F3, the idea was trying to basically maximize, and based on that we discussed the Pareto and the indifference curve and the movement being in the parallel direction and Pareto points also. Now, consider you want to decrease F3. So, decrease F3 basically if I consider the point 2, the value 2 for so F2 can decrease, and as an example it becomes 1. Now, if I am trying to basically find out the minimum for all of them, remember for F1, F2, F3 separately, then minimizing F1 from F3 from 2 to 1 is fine. But let us see what are the consequences, because the sets which are applicable such that x1, x2, x3 all add up to 3 has to be maintained. So, F1 stays at level 2 as I am marking with red, I will use a different color, consider I use the violet. So, this is maintained, 2 remains 2. But what happens to F2? F2 rather than decreasing from 2, it increases from 2 to 4, which I am now marking in blue. So, it was initially 2, now it becomes 4. So, what is the overall effect? Overall effect is for the value that rather than getting a sum of 6 which was here, now the sum 7 becomes 7. So, obviously, it is not desirable. Now, if I consider on the other hand this set, so say consider I will erase the colors. Here the same analysis thing happens, F3 decreases on the another way is goes to 2 to 1, here F2 remains at the same level 2 and 2, but very interestingly it is not F2 which is being affected, F1 will now increase from 2 to 4, hence the sum of them now increases from 6 to 7. So, if I consider the 2 mark points which are green, which is 7 here, 7 here, total value is 7, same. So, the set of points 2, 4, 1, 4, 2, 1, they collectively give me the same points. So, if I consider on a 3-dimensional space, their sum, 3-dimensional space means I am considering the values of f1, f2, f3 and then trying to plot it, but actually we will consider the answers of the decision variables separately. The value 7 remains same, and if I consider the set of points which is 2, 0, 1, 0, 2, 1, collectively they can be considered as Pareto points, because the sum of the functions f1 plus f2 plus f3 remains as 7. So, no one is better, in the sense sum is 7 for f1 plus f2 plus f3, and what combination you will try to analyze the problem would depend on what is the combinations of decision variable output which is possible for you. Now, consider the idea of this example, where the movements are minimization again. Now, you are moving from 9 to 4, and the 9 moving from 9 to 4 are given in 2 different instances, 2 different examples. So, I am not going to consider the example for yellow or dark yellow or light orange, whatever you say, for the second one, which I am putting a mark. So, the same analysis will be repeated. So, I am not going to repeat that, and for this I am not going to say anything, because whatever I will now mention can be replicated similarly. So, erase these blue points. So, let us consider the analysis using, say for example, the violet color. So, now 9 has to decrease, minimization, it decreases to 4. So, obviously, the sum value comes down 7, 7, which is fine, but interestingly see that the total sum comes down to 6. In the other case, it has increased, because compromising, trying to bring down f3 was fine individually, but we saw that it resulted in the overall collective sum being increasing. Now, here the f3 value is decreasing from 9 to 4 in one case, and another instance again 9 to 4. So, this is instant 1, case 1, this is case 2. Sum going from 9 to 7 total is good, sum going from 9 to 7 total is good. But on the other side, see very interestingly, total sum is reduced, but individually f1 and f2 have increased. How? 0 has increased in one case to 1, and another case it has increased to 2. Similarly, f1, 0 has increased to from 0 to 2, another case it has increased from 0 to 1. So, the combination which are giving this value 7 are like this. I will mark it here. One is the decision variables which are giving me this answer for 7 is x1 0, x1 x2 1, x3 2, another is x1 1, x2 0, x3 2. So, collectively if I consider, the sum is 3 based on the constraints, perfect. The functional value of f1 is now 2 and f2 is 1, another case is f1 is 1, f2 is 2. The value of f3 has decreased from 9 to 4 in both the cases, sum is 7, which is fine. So, if I consider this, they are technically Pareto. We have been able to reduce the total value from 9 to 7 in each of the cases, but the combination f3 is fixed, but f1 f2 have been changed. That means, they are trying to compromise in order to maintain the balance at a value of 7, which is sum of f1 f2 f3. So, the analysis which I did or which I mentioned would all be repeated if I did these. So, here the value of say for example 9 can decrease to 7, can decrease to 7 in both the cases, total sum 9 decreasing to 7, which is perfect. F3 value is maintaining its position, it's in one case is increasing its position. That means, for trying to bring down the total sum of F1, F2, F3 to from 9 to 7, it is increased from 0 to 4. So, it was initially has decreased from 9 to 4, here it is increased from 0 to 4. And if I consider the values, so the values are here F2 was 0, it would either increase to 2 or increase to 1, and F1 was initially 9, it will basically decrease to 1 or decrease to 2. That means, in all these three instances, the sum is being decreased, total sum F1, F2, F3 from 9 to 7 in two different cases. So, I will consider this as case 1, this as case 2. So, but individually if I see F3 has increased from 0 to 4 in both the cases, case 1, case 2. F2 has increased from both the cases individually separately from 0 to 1 or 0 to 2, but F1 which was initially 9 has decreased in both the cases substantially to 2 or 1, such that the sum of F1, F2, F3 is being maintained at 7. So, in this case if I consider 7, 7 where the sum of F1, F2, F3 is 7, it is Pareto optimal. The combination of points which is resulting this for x1, x2, x3 are these 0, 1, 2, then 1, 0, 2, which is fine, and the set of points which are optimal for the concept of F1, F2, F3 are 2, 1, 4 and 1, 2, 4. So, based on that I can also find a functional form of the decision variables of F1, F2, F3, which is resulting in this optimum solution. So, we will consider the concept of goal programming, which is basically we did discuss, but I will highlighting it further on. Discussed in the sense that we mentioned and briefly, and I said that I will be visiting that with the problems. Is a branch of multi-criteria decision making or MCDA, which was introduced in 1962 in the deployment of the antenna system for the Saturn Apollo moon landing system. Goal programming as a technique is a useful and effectual tool for modeling, finding solutions and analysis of mathematical models that involve multiple and conflicting goals and objective type of models, where as you have seen in the problems, many of these compromises have to be understood in order to basically maintain the level of the collective goal. In many linear programming problem, obviously we will consider later on for nonlinear programming also, objectives may not be single, but multiple objectives, plus they can be soft as well as rigid constraints based on which we will try to analyze the problems. To take care of multi-objective models, one has to measure the goodness of the solution, how good it is. So, whether it is able to meet all the criteria, whether it is a compromise solution, whether it is optimal, effective. So, that is the main answer. Minimizing the profit to the or maximizing the loss, if we consider, there can be situations where rather than trying to basically, when I mentioned the concept of minimizing the profit and maximizing the loss, would be the cases where, say for example, I minimizing the profit in the sense I have to run the factory, but the overall sales of the product is very low. So, I will try to basically maintain the minimum production such that my minimum profit is maintained, because if I stop production, so obviously all the salaries, all the electricity bill, the pension, the gratuity, whatever is to be paid, the security, the rent, everything has to be paid as per the norms. So, if I maintain a minimum amount of production, I may be able to reduce my loss such that in some way I am trying to maintain the minimum level of profit which is required. Any more production may, either I stop my production, which means this total loss, or it may happen in many of the cases for any further production levels, because if the goods are being not sold, there may be instances that they may be piled up in inventory, which means for more number of production, because I am paying labor cost on an extra hour basis, like giving overtime, trying to basically buy raw materials, trying to utilize extra electricity, that may entail that the situation may be become much more worse, such that rather than maintaining that minimum profit, it now become a loss. To take care of multi-objective models, one has to measure the goodness of the solution, that is to transform the objectives into goals which are achievable by means of establishing an aspiration level or a target level. Consider objective function is of maximization or minimization type, then the converted model will result in 3 states of solutions, which are less than optimal, more than optimal, or exactly equal to the optimum value. So, what you want to achieve is basically optimal solution, but what is doable under the present circumstances, under the practical situation, have to be considered. It is evident that in the former two cases, one has to minimize the undesired deviation. More than optimal, reduce it. Reduce in the sense that if your optimum value is, I will come to that, if your optimum value is 10 and if produced more, which means that producing more, obviously you would not be achieving the optimum value, you exceeded, you produced more, which means the cost price is more, even if the selling price is there, but the cost would be increasing at an increasing rate, such that selling more and more, obviously you will be going into the negative region. So, you will try to bring it down to the optimum value. While if you produce less, it may be the case that any delta amount or extra amount of production may increase your profit, the difference between the revenues and the cost, and bring it to the optimum level. So, in which way you want to operate, you have to basically understand. So, let me continue reading it. It is evident that in the former two cases, one has to minimize the undesired deviation, which can be tackled following the 3 forms of geometric goal programming. One is the Archimedean concept, also known as min sum or weighted concept, where one is to seek to minimize the weighted sums of all the unwanted absolute deviation from the goals. So, there are deviation in the goals, you want to minimize them, and you give weights depending on what are the level of negative or positive importance you want to give to these deviations. Chebyshev's concept, also known as the min max one, where one desires to minimize the worst or maximum of the unwanted goal deviation. So, if you remember the Chebyshev's inequality or the Chebyshev's bounds, which were considered under the safety first norms when we are discussing utility theory. Non-Archimedean concepts known as the preemptive priority or the lexicographic norm, where one seeks the minimum, more precisely the lexicographic minimum of an ordered vector of the unwanted goal, such that you want to basically reduce your loss or try to increase your profit to the maximal level. When I am using the word profit and loss, it is in very general sense. Positive, something negative is a loss, something positive is a profit. Linear programming as well as Archimedean and Chebyshev's concept may also be considered as special cases of non-Archimedean goal programming ideas. So, I will first consider the general concepts of the ideas of goal programming and then consider slowly different type of examples. The problem is trying to maximize a function f 1 or f I, which I will mark in blue, and there I want to also maximize g j where I and j are different. X is the set of decision variables which is of n dimension in the n space, and the corresponding constraints are divided into 3 sets. One is greater than type, which I will mark with greater than type, which I will put a 1 tick mark in red. The second one is equal to, which I will put a 2 tick mark in red, and third one is less than type, which I will put 3 tick mark in red. So, what is the constraint? Constraints are basically of less than type is k 1 in number, equal to is k 2 in number, less than type is k 3 in number, such that k 1 plus k 2 plus k 3 is equal to capital K, the total number of constraints which are there. Now, there can be instances where greater than type does not exist, there is only equality and less than type. There can be instances when equality does not exist, only greater than type, less than type. And another case can be where when you are considering at least 2 combinations are there, when less than type is not there, only greater than and equality is there. The simplest would be where only greater than type is there, equality to less than type is not there, only equality is there, greater than type, less than type is not there, and finally, less than type is there, greater than inequality is not there. Now, what are the constraints? Constraints, if you see, we have considered in a very simple way. The k 1 number of greater than r, h 1 is a function, h 1 k 1 of x is greater than b k 1, b k 1 is basically a value, deterministic one. Equality type is h 2, again a function, k 2 in number of x is equal to b k 2, again b k 2 is the set of constants. So, and finally, h 3 k 3 x, x is the decision variable less than or equal to b k 3, again b k 3 are constant. So, k 1 can be 2 in number, k 2 can be 3 in number, k 3 can be 4 in number. So, it is 2, 3, 4 is basically you have 2 plus 3 plus 4, which is 9 number of decision variables. We will consider the concept of goal programming later on with examples as we proceed. So, with this I will end this 30th lecture and discuss further on about the ideas of goal programming. Thank you very much and have a nice day.